Hello everyone, my name is Xinchen Hao. So today I will discuss about the appendix A, which is the load estimation in our project. So first of all, the table over here, this is the appendix A, which consists of three divisions, division 1, division 2, and 3. So each of the division has its own load. Then of course, all the load we have to calculate and we have to get the maximum demand. So without further ado, let's see the first step to get this load estimation. So first of all, we have to calculate the total connected load in this three division. So in order to calculate this total connected load, which is the apparent power for this load. So the first thing first is we have to get the real power in the unit of kilowatt. So since we know each of the motor, we get the horsepower, then we know that 1 horsepower is equal to 0.746 kilowatt. So we can simply get the horsepower and time by 0.746. Then we can get the real power at this part of this model. So next, we have to get K, which is we just simply multiply the power factor with this efficiency, then we can get a K. So we get two of the result, then we can calculate the apparent power in the unit of kilowatt ampere, which we just simply get the real power and then we divide by K. So at this column, this is the value for this apparent power for each of the load. So after we total all together, the total connected load in this three division is 5,737.205 kilowatt ampere. Done in calculating the total connected load. So next, we going to the load estimation. A little bit complicated. This, since we have to estimate for KU and KS. Okay, so to calculate this power in estimation, so first we have to move the apparent power that we get from the previous calculation to this part, and we have to estimate the utilization factor KU. KU actually stands for the power total connected load with respect by time. So since this is the induction motor connected as a load, so the utilization factor will be estimated as 0.8. So for the lamp load and the lighting, we'll consider as 1. So this one, motor, of course, will be 0.8, and the MCC will be considered as 1. So to get the next apparent power, which is considered as maximum demand, after we consider this utilization factor, you get the utilization factor, we times by this apparent power, then we can get this one, this answer. So after we get this one, and we have to consider another factor, which is we call as a diversity factor. So how can we get this diversity factor as 1, since this induction motor, the power of this induction motor is more than 100 kilowatts, so it's considered as 1. And same as lamp load and heating and lighting. So of course, the diversity factor is considered as 1. And we have this division number 3, the synchronous motor and the MCC. Since all of them is more than 100 kilowatt, so the diversity factor have to consider as 1. So to get this apparent power, we just sum all of these and we multiply by the diversity factor, then we can get this answer. Same go to this one and this one. After we've done the math, and this is the value that we will get. So after done for this division 1, 2, 3, okay. So we have to do for a non-diversity factor, since we have another transformer which is T1. So to get T1, the estimate sizing for T1, so we have to add on all of these together, and we times by this diversity factor number 2, which is the value is 1. Then we can get this uh, estimate maximum demand for transformer T1.
Very good day to Dr. Nadiana. My name is Daniel Gangifat, AD1900. Today I'm going to do a presentation on project methodology of industrial loadings. And for our distribution system general layout that we are going to take care for the preliminary designs, that there are a few factors that are taken care of, which is terminal sizing, cable sizing, signal diagram layout, and line device characteristics. So for our flowchart of project planning, which is from the compute of industrial load data to feasibility and reliability study, then we're going to perform a load estimation, terminal sizing, decision on the cable sizing from 3 divisions, and after that we're going to heading on to the expansion of the 60% for our existing loading, and in the end we're going to sketch one another. Okay, for the decision of proposed material loading, we're going to the transformer core materials and the cable core material is a factor that we're going to consider. For losses that in the distribution transformer, which we're going to use is P with I square. For the table 1, we're going to construct it based on the location of loads, load device, and load characteristics. So for the distribution of the proposed industrial loading, we have a main incoming transformer T1, which is the 3 kilovolts, and there are 3 bus bar and 4 transformer. The T4 and T5 is under division 3, which is 1 division, and the loading over here is specified in Appendix A. So for the next is the expansion of power system, which is we have 2 methods of here, which is the 3 kilovolts and to the 11 kV bus bar, 5 bus bar, and under 1 central transformer. And the other methods is 2 independent transformer, which is the original one, and 60% expansion is another expansion. And both of these have pro and cons, which are illustrated in the words here. So that's it for my presentation. Thank you.
Very good afternoon. My name is S4G5. My meeting number is AE190093. I am a session 4 and group 5 members. So today I'm going to discuss about the transformer and cable sizing. First, I want to discuss about the transformer sizing. So step 1 is calculating the maximum demand for each division, and step 2 is referring to the technical specification of standard transformer, and then step 3 is comparing the calculated maximum demand with the standard transformer, and step 4 is choosing the suitable and rated standard transformer. And then step 5 use this formulas for calculate the rated current for each transformer from T1 and until T2 until T5. So step 6 is calculate the short circuit currents. After we'll use short circuit current for calculating the cable sizing. So and then capacity, short circuit current, we use this formula calculate for each transformer T1 until T5, and then we also multiply the short circuit current with the minimum is 10. We also can increase it for the purpose of safety and precaution. So last for the transformer, for the selection of transformer sizing. Last step is calculating the short circuit capacity of transformer by using Excel. Later I'll show it how to. Later I'll show it the Excel. Okay, this our the calculation for the transformer sizing, and then we use apply the formula I rated current, short circuit current, and also the multiply with the short circuit current will multiply the safety and precaution for for get for getting the short circuit capacity. So this appearance curve refer to the load estimation, and then this I read, and this is referred to the table. standard transformer, and then we will calculate out the I-rated, and then also after I-rated calculate out, we use I-rated to calculate the short circuit current. And multiply by the setting agriculture, and then we get the short circuit capacity. So we also apply 60% expansion at the T1 and then the T4. We apply it at T1 and T4. So next is cable sizing. Cable sizing step 1, we calculate the cable sizing for division 1, 2, and 3 by using Excel. So we use this formula. So this short circuit currents we get from previous one. From the previous one, and then step 4 is referring to the standard dimension of insulation material. Step 2. Step 3 is choosing the SPLE or EPR for fundamental of the cable requirement, and step 4 is the calculation of subcircuit temperature rise constant K. So we also step 5 is applying subcircuit current, which are multiplied by the minimum 10%. Minimum 10%. Sorry. Minimum 10%. 10 times, sorry, 10 times. Sorry, step 6 is calculation of the duration of the circuit in second. So frequency is in Malaysia is 50 hertz, and then step 6 is calculation of this is step 7. Step 8. Step 7 is a calculation of cable sizing for each division, and then step 8 is referring to the centered cable sizing. Step 9 choose the rated suitable of standard of suitable of cable sizing. So let me show the cable sizing calculation. So first we calculate out the K for each copper aluminium. So this get from the previous one. So we calculate the area using the formula, and then we calculate both, and then we can refer which one is suitable for is copper or aluminium. These two table, one is copper, this one is aluminium conductor standard size, and then this one is copper conductor. So we refer to this and choose the standard one from our calculation. Okay, this is all for me. Thank you.
A very good morning to all the lecturers who is watching this video presentation today. And now I'm going to present with you about the parts of outcome for the load demand estimation. So for division 1, I have first 400 horsepower induction motor. The voltage rated is 3.3 kilowatt, and the power is, as said just now, 400 horsepower, and the efficiency is equals to 84%, and the power factor is 0.85. Well, we need to changing the power into a watt. So 1 horsepower is equal to 746 watt, and then the nominal power rating is equals to 400 times 746 watt, and it was equals to 200 plus kilowatt. And after that, we'll calculate the apparent power by using the formula given, where the apparent power as is equals to the kilowatt over a power factor times the efficiency. So here is the value that we can get. It is 417.927 kVA. And after we find the apparent power, we need to do the apparent power demand maximum, where's the X max, the apparent power times the utilization factor, KU. And the KU selected is 0.8, which is the common value for motor in industrial power system. And then the S max we will get is 334.342 kVA. And next is the induction motor with different horsepower, and the apparent power we get is 900 is this value, and the maximum will be the 736.79 kilo VA. And third is the induction motor with different horsepower, which is 1500 horsepower, and efficiency also is not the same, which is the 93%, and the power factor is 0.92. And here is the apparent power, 1307.854 kVA, and the maximum is 1046.283. Now we continue to the division 2, where the division 2 we have a load pump with a V rated of 0.415 kilovolt, and the apparent power is 600 kVA. Since the S is given, so calculate the apparent power demand maximum, where it is times KU, which we selected 1.0 due to the assumption made, which the load will be utilized 100% of power rating after turning on the switch, so it will be 600 kVA. And not only the lamp load, sorry, heating and lighting also included in division 2. And the apparent power is given already, so we need to calculate the maximum. KU selected also 1.0 is also due to the assumption made, where it will be utilized 100% after switch on. And next is division 3. At first we have a synchronized model with 1250 horsepower, efficiency with 78%, and a power factor of 0.86. And the apparent power is 1390.131 kVA, and the maximum is 1112.105 kVA. After that we have MCC 1 with efficiency 80%, PF of 0.81, and we will get here as the power apparent power, and the maximum is 518.056. And third element is induction motor with a 250 horsepower, efficiency of 82%, and power factor is 0.79. Here is the apparent power and the maximum demand. The fourth element is the MCC2 with 250 horsepower, 85% efficiency, a factor of 0.83, and the efficiency and the apparent power is 264.325 kVA, and the maximum demand is also the same because we choose KU as 1 due to the 100% utilization. And after that, we are going to find the total maximum demand, and they have two levels. We need to find it. The first level for division 1, the KS we need to use is 1 due to active power summation of the induction motor 1, 2, and 3 is greater than 100 kilowatt. So where we need to add up all the induction motor power. After that, we use the power of connected outgoing times the diversity factor, 1.0 KS, and we will get the maximum total maximum. For deviation 2, KS is also the 1 due to heat and lining, and also the lamp load is utilization of 100% power rating after switch on, so it will be the 630. For division 3, is all the same because the active power of the motor is greater than 100 kilowatt. And MCC1 induction motor, MCC2 is also KS. We choose 1 because the active power of the motor is greater than 100 kilowatt. And for level 2, the diversity factor is chosen is 1 due to the efficiency of distribution to make it more efficiency and more reliable. So the total up and we added times with 1.0, and we will get 4,872.245 kilo kVA. And according to the one-line diagram, there are 3 divisions, 1, 2, 3 are each, which is made up of 5 transformer, T1 to T5, and the calculation for load estimation has 2 levels, level 1 and level 2. Level 1 use a diversity factor of 1 because the motor is greater than 100 kilowatt, and other loads will use 100% of their power rating once turned on. And level 2 is also 1.0 because it is assumed that the distribution system is operating at full capacity. And the utilization factor used in the calculation is 0.8, which is the same for all models, and 1 for other loads due to the utilization of 100% power rating after turning on. And next, about the outcome of industrial network design. The architecture of the power transmission network is depicted in the diagram above, and in accordance with the client's request and the distribution of load demand to reduce the high voltage to desired voltage and protect the equipment in the event of an indirect wire connection problem. Each division is linked to a single transformer. The main distribution transformer received from the main Tenaga National Berhad supply, which is then solely divided into 3 divisions, and the PCC, point of common coupling, in this instance is the bus duct system, which is connected to the secondary side of the main transformer. And the power transmission was then divided in 3 sections, each of the transformer and the same rated primary voltage. The voltage of each division is then stepped down by referring to the load requirement. However, 2 required voltage apparel in the 3rd division, which is 6.6 kilowatt and 0.14 kilovolt, which cannot fulfilled by only 1 transformer. So therefore, another transformer is needed and to be installed below the 3rd division to provide another low voltage level for the particular load. That's all from me. Thank you very much.
Hello and Salam Sejahtera, Dr. Nodiana. I am Kunchan Phai with the matrix number AE190091 from Section 4, Group 5. In this part of the video, I shall be presenting the results and discussions on the transformer and cable sizings that we have chosen for this assignment. First up, with the transformers, which includes the mains, incoming, and distribution transformers. So I shall be explaining the mains incoming transformer T1 first. So transformer T1 has a total apparent power needed to supply, which is 4,872.25 kilovolt ampere. The power rating chosen for this transformer is 10 megavolt ampere with an impedance voltage of 6.3%. The cooling class that we have chosen for this transformer is oil natural, air natural, Onan type. The rated current, short circuit current, and the short circuit capacity are 255.73 ampere, 40,591.52 ampere, and 773 megavolt ampere respectively. Next, we shall come to the first distribution transformer, which is transformer T2 in division 1. The total apparent power needed to supply by it is 2,117.42 kilowatt ampere. The power rating chosen for this transformer is 2,500 kilowatt ampere with an impedance of 6.5%. And the rated current, short circuit current, and the short circuit capacity are 370.45 ampere, 102,586.59 ampere, and 586 megavolt ampere respectively. Next, we have transformer T3 in division 2, which is a distribution transformer as well. The total apparent power needed to supply by it is 630 kilowatt ampere. The power rating chosen for this transformer is 750 kilowatt ampere with an impedance of 6%. The rated current, short circuit current, and short circuit capacity are 576.56 ampere, 306,760.81 ampere, and 221 megavolt ampere respectively. Next, we have distribution transformer T4 in division 3. The total apparent power needed to be supplied by it is 2,124.83 kilowatt ampere. Power rating we have chosen for this transformer is 2,500 kilowatt ampere with impedance of 6.5%, as the same as the one that came before this. The rated current, short circuit current, and short circuit capacity are 185.87 ampere, 51,472.92 ampere, and 588 megavolt ampere respectively. Next, we have distribution transformer T5 in division 4. The total apparent power needed to be supplied by it is 1,408.91 kilowatt ampere. The power rating chosen, we have chosen for this is 1,250 kilowatt ampere with an impedance of 6%. The rated current, short circuit current, and short circuit capacity are 1,408.91 ampere, 234,818.11 ampere, and 169 megavolt ampere respectively. Since in the assignment we were given the task of future-proofing the industrial power system, hence we needed to take in consideration of the total load increment of 60% in comparison of the current loads that have been given. Hence, thus, our group decided to add a mains incoming transformer, which would be supplying 7,785.59 kilowatt ampere. The power rating chosen is 10 megavolt ampere with impedance voltage of 6.3%. The cooling class is oil natural and natural, own and type. The rated current, short circuit current, and short circuit capacity are 409.16 ampere, 64,946.43 ampere, and 1,237 megavolt ampere respectively. And we would add another distribution transformer as well. So the total apparent power that will be supplied by it is 2,732.47 kiloampere. The power rating chosen for it is 2,500 kilowatt ampere with impedance of 6.5%. The rated current, short circuit current, and short circuit capacity are 239.03 amp, 66,192.56 amp, and 757 megavolt ampere respectively. Now we come to the cable sizing. Cables are the integral part of the industrial power system as well, as they connect all the transformers, all the components together. So for the first one, the first cable 1 in division 1, which serves the distribution transformer T2, the rated current of the transformer is 370.45 amps. Hence, we believe that the appropriate cable sizing for this cable is 120 square millimeter single core copper conductor cables that are touching. This is because the current carrying capacity of the cable is 400 amps. Next, for cable 2, in division 2 that serves distribution transformer T3, the rated current of the transformer is 874.46 amp. Hence, we believe that the appropriate cable sizing for this cable is 400 square millimeters single core copper conductor cables that are spaced out horizontally. This is because the current carrying capacity of the cable is 185 ampere. Next, cable 3 in division 3 that serves distribution transformer T4. The rated current of the transformer is 185.87 amp. We believe that the appropriate cable sizing for this cable, we have found out the cable sizing for this cable is 70 square millimeter single core copper conductor cables. They are touching. This is because the current carrying capacity of the cable is 279 ampere. And again, since we were given a task to future-proof this industrial power system that would have a total load increment of 60% in comparison of the current loads that had been given. So this is for future-proofing. Hence, we have added one cable for the transformer that was added for future-proofing as well. The rated current of that transformer is 239.03 amp. Hence, we believe that the appropriate cable sizing is 70 square millimeter single core copper conductor cables that are touching. This is because the current carrying capacity of the cable is 279 ampere. Okay. That is for the results and discussions part. Thank you. Now I shall present the environment and sustainability issues, and we'll be proposing a few solutions to these issues. Since building a industrial power system can bring a lot of environmental issue, we need to be mindful of our environment and remember the importance of sustainability so that we don't destroy the environment when we build these power systems. Transformers can be a detriment to their surroundings if they are not maintained properly, and they will become inefficient over time. Thus, important environmental protection measures must be taken to reduce the negative impacts of such electrical machines. Firstly, poorly maintained transformer will be less efficient, and this can cause unnecessary energy loss and increase failure rates. Speaking of failure rates, as technology progresses, implementing better technologies such as electronic instruments can assist in elongating the lifespans of these transformers, as well as optimizing them. Furthermore, transformers currently use insulating oil as their cooling medium, which are mineral oils, which is non-biodegradable and can bring havoc to its surrounding environment. Hence, shielding and proper drainage systems needed to be installed to ensure that in the event of a massive leakage and spillage of the substance due to the unforeseen failures, these drainage systems can safely divert the oil away into a draining pool instead of the environment. Finally, we have noise pollution. Noise pollution is an understated pollution for all of human activities, as humans create a lot of noise when they are developing structures and cities. And transformers are unavoidable as well. Transformers can emit deafening and unpleasurable noises when they are in operation. Proper sound barriers and noise insulations are needed to be implemented to the transformers to reduce their noise output during operation, as they can cause disturbance to the surroundings, such as residential areas and business centers. All right, that is all for the issues and proposed solutions. Last but not least, we were given a chance to talk about the weaknesses of the proposed design as well. No matter how advanced and intricate the short-term planning can be, there are still weaknesses that will present themselves over time, and there will always be room for improvement. For example, one of them is the load power demand of the industrial sector will slowly increase throughout the years as human activities increases. The industrial sector consumes the largest amount of electrical power, and the power they consume will still increase from their current consumption. In the past, increasing electrical power supply and demand can always be satisfied as long as people are willing to pay. But as we enter into an age where sustainability becomes an important part of life and non-renewable sources are getting scarcer by the day, long-term future planning is needed for transformers and cables that makes up the industrial power network system to extend their lifespan and provide an even longer service time before needing for replacements. Since the load demand will increase, power supply must be sufficient to reach demand, but at the same time, people and companies cannot afford to be wasteful in spending money and resources in attempting to achieve the impossible. Reliability and maintainability is important for the power system to go a long way. Other than that, keeping efficiency assumed to be the best would also make design hard to be converted into the physical world, since the design and real life are two different things. Application in real life and the assumption won't be the same, and this may cause people confusion. Furthermore, opinions on cable sizings can also be different when comparing with different data collected from the field by different individuals. However, real-time data does help in a more intricate analysis of equipment to be used to reduce waste of resources and funds. I believe that is all from us. Thank you very much. As a conclusion to this entire assignment, we have learned about the intricacies in the planning and producing of a suitable industrial power network with industrial loadings that have been given in the assignment. Through this project, we were able to estimate the sizing of transformers for incoming power supply, as well as the distribution of the power supply to the estimated industrial loads, along with the cables that are serving in their respective divisions. We have been exposed to the subject by learning to create an appropriate industrial power network without wasting resources and energy that sacrifices efficiency. Moreover, we were able to perform all of that by analyzing the industrial power system by taking consideration of energy resilience for specific loadings that will be served by the transformers. Through this assignment as well, we were able to perform an assessment on future power usage that will be used and provide an estimation of that load increment along with the transformers and cables that serve the transformers. Finally, we were able to successfully design an industrial electrical system with the environment in mind as well as sustainability concerns. Thank you.